Hey everyone, this is Dr. Brian MacDonald, author of Practical Stress Analysis with Finite Elements. It's the book, which is a great introduction to finite element analysis, so I'd encourage everyone to buy it. And today we're going to be looking at an axisymmetric analysis. So we're going to be doing an axisymmetric analysis of a stepped circular shaft using ANSYS Workbench. So first of all, let's just take a look at the problem. So we're going to examine the axisymmetric distribution of stress in a stepped shaft of circular cross-section loaded in simple tension. So here's our stepped shaft here. So we have a larger diameter up here of 0.2 meters, and we have a height reduction of 0.075 meters, a radius here blending between the two different cross sections of 0.025 meters, and we've got a tensile load of 1000 newtons on the end of the shaft. We're told that the shaft is made from steel with a Young's modulus of 210 gigapascals and a Poisson's ratio of 0.3. And what we're asked to do is find the maximum stress in the shaft, or the stress distribution in the shaft. So first of all, just using simple theory, we'll know that the stress in the shaft is applied load divided by the cross-section area. So for the shaft, the nominal stress on the smaller diameter portion, so down here, the stress is going to be load over area, so that's going to be 1000 over pi r squared, and in this case the radius is 0.025. Again, where are we getting that from? If you take 0.2 meters and you take away 0.075 plus 0.075, you get 0.05. Divide that in 2, you get 0.025. So if we work all that out, we find that the nominal stress is about 0.5 megapascals, or 500,000 pascals. So that would be the stress in just this portion here. So obviously we have a fillet here, and that fillet is a stress concentrator. So we're going to get a higher stress around this region where we have the change in area, and probably around the fillet here. So if we go and look up stress concentration factors, we can find a stress concentration factor for the axial stress in a stepped shaft in tension. So you get these curves here, if you look this up from a book of tables, and you'll see that the curves are, first of all, it tells you how to work out the nominal stress. Okay, so the nominal stress is as we've just worked out there, so it's the load over the cross-sectional area of the smaller portion, and you can rejig that to give you 4p over pi d squared. We worked in terms of r, so that's where we didn't have the 4 above the line. So we've just worked that out, and then we can find out, well, what you need to do is you need to find d over d, which is the bigger diameter divided by the smaller diameter, and then you also need to find r divided by d, and r is the radius divided by the diameter. And if you plug them both into this curve here, you can find out, first of all, which curve you're dealing with, and then you read off r over d. So let's say, for example, your d over d was 2 and your r over d was 0.1. You'd go up here and you find this point here, and you'd find that your KT value, or your stress concentration factor, was 2. Okay, and what you do then is you'll multiply your nominal stress by that stress concentration factor, so you double your nominal stress, and that would give you the stress at the blend region here. In our case, our d over d factor doesn't fit into any of these curves here, so if you go and investigate this further, you can find out that the curves are represented by this relationship here. Okay, so the stress concentrator factor K is equal to a constant C1 plus a constant C2 times 2h over d. So again, just going back to the previous slide, that's that h there, and there's the big D there, the larger diameter. Again, we have another constant 2h over d squared and another constant 2h over d cubed. These constants then are given, basically are a function of h over r. So we can plug all our values in here, and we can find out what C1, C2, C3, and C4 are. We can plug in 2h over d in there. We put all of that in, and we find in our case our stress concentration factor is K is equal to 1.37. So that means that the maximum axial tensile stress in the shaft at the fillet region will be 1.37 times the nominal stress we just found, which was 509,000 pascals, which gives us about 0.7 megapascals, so 697,735 pascals, or 0.7 megapascals. So that's the the value we're expecting to find. This is the value we're going to validate our finite element analysis results against. Okay, so when we do our FEA correctly, we should find that we're getting a maximum axial stress in the shaft around the fillet of about 0.7 megapascals. So let's talk about the kind of analysis we're going to do then. We're going to do an axisymmetric analysis. So what an axisymmetric analysis is let's just take a very simple example of a cylinder subjected to internal pressure. So if we have this simple cylinder here subjected to internal pressure, if we were to take just a slice through the wall of this cylinder here, we can model just this two-dimensional slice, and once we give it an axisymmetric formulation to the elements, or in other words use axisymmetric elements, then the FEA software will see that slice as being swept around 360 degrees. So this is our real cylinder, and this is what our axisymmetric model of this hollow cylinder will look like. And you can see that the y-axis is the axis of symmetry. So in most FEA software, you'll find the y-axis, the axis of symmetry. In Workbench, that's what it uses as its axis of symmetry. So for us to make this hollow cylinder here, we would have to build a rectangle at a certain distance away from the y-axis, which is equivalent to the internal radius of the cylinder. Okay, and as I said before, it assumes that that rectangle and the applied load is swept around 360 and generates the entire cylinder. Again, this is just the same thing, kind of put in a different way. This is showing us, well, if you wanted a hollow cylinder, you would have to move your rectangle a distance equivalent to the inner radius of the cylinder away from the y-axis. If you didn't do that, if you took your rectangle and put it on the y-axis, what you'll actually get is a solid shaft. Okay, because it sweeps it literally around the y-axis. So if there's a gap, the gap will also be swept around, giving you a hollow cylinder. If there isn't a gap, you will get a solid shaft. So in our case, we want this one. We want the solid shaft. We want to step in it. So here's a picture of what our geometry is going to look like. So you can see there's our y-axis there. And again, it's important to note that it's always swept around the y-axis. So if I did the geometry in this direction, that would be incorrect. Okay, so here is my larger diameter there, here's my smaller diameter, here's my radius, and this is the finite element model that we're going to end up with. You can see we get a stress concentration. So the red area there is the high stress. This is a plot of axial stress, and so again stress in the vertical direction, and you can see we're getting a high stress where we'd expect it there around the fillet. Okay, so let's just go to Workbench and start working through this. Okay, so I have Workbench open here, and I've already saved my model into the temporary directory on my computer, and I've given it a name of axisymmetric step shaft. Again, you can call this whatever you want. Okay, so I've already done that. We're going to do a static structural analysis. Okay, so we go down to static structure here, we right click on it, and we grab it, drag it across, and drop it here. Okay, so now once that's there, again, the first thing we always do is we go in and set up our engineering data. So let's double click on that. Again, we can see there's already structural steel in there, but it's got slightly different properties to the properties that we want. So I'm just going to add a new material, and we're going to call this, again, just my steel. Doesn't really matter what you call it. So my steel is there. Double click on isotropic elasticity. Go down to Young's modulus, type in 210 e to the 9, underneath to Poisson's ratio, and go 0.3, and enter. And now we've set up our material model. We don't need to set up anything else for that. Okay, so we're going to be using my steel. So again, maybe just a quick save there, and we can then close down the engineering data box. The next thing we want to do is go to geometry. So we click on geometry. And the first thing we're going to do is come over here and click on 2D. Okay, so we want to have a two-dimensional geometry. So this step is very important because it's hard to change this later on. Okay, so again, if this box isn't showing up for you, again, you can just right click on geometry and click on properties, and that will show up there. And again, you may need to scroll up and down here, but it's advanced geometry options and 2D. Okay, once that's done, right click on geometry again and go new design modeler geometry, and then we'll just wait for the design modeler to open up. Okay, so here's my design modeler opened up now, and what I want to do now is I want to do a sketch on the XY plane, and remember again my geometry has to have the axis of symmetry in the Y. So I'm going to click on XY plane here, and then I'm going to click up here and say look at the plane. Okay, and now I want to do a new sketch on that XY plane. So if we just quickly jump back to take a look at our problem, so you can see that our problem has a outer diameter of 0.2 meters, which means it has an outer radius of 0.1 meter, and again it has this radius here ends up being 0.25 meters, and again we have a radius of 0.025 as well. So our maximum diameter or our maximum radius here is 0.1 of a meter. Okay, that's our biggest dimension. So what I'm going to do is I'm just going to go in and set in a grid, show the grid in 2D, turn on the snap, and the major grid spacing, I'm going to put that in as 0.1 of a meter. Again, just to ensure that you're using the meter unit system up here, okay, meters and degrees. Okay, so you can see, so I can't even see my grid because I'm so far out, so I'm just going to hit down the control, use the center mouse key and zoom in there until I start to see the grid. Okay, so there's my grid, and each one of those is 0.1 meters. Okay, so now I can start drawing my model. It's going to start off, I can use a line or a polyline here. I'm just going to use a line to keep it simple. I'm going to turn off the selection filter here, so it just uses points. Okay, so I'm going to put a point there. I'm going to go across here. My grid line here is set to 0.1 of a meter, so I know that that's 0.1. Again, I'll maybe go up maybe twice that. Okay, I've done another line, and again I want to just going to pan that down a little bit so I can see more of it. And again, I'm going another line here. Click on line again. So here again, it doesn't really matter if I get this right or not. I'm going to go in and dimension it later. And again, so I've just drawn a rough outline there. Okay, so the next thing I'm going to go into use modify. I'm going to go fillet, and I'm going to click that line. Now, first of all, I'm going to go up here and change my fillet radius to the one from the problem, 0.025 meters. Okay, and then I'm going to go there, click those two lines, and there is my fillet in there. So now I'm just going to go back to dimension, and I'm going to go horizontal first of all. So I want to get, again, I'm going to change this to just select points. So this point, and drag out my dimension. You can see it's 0.1 meter, which is what I want. And then I'm going to do the same up here. Another horizontal one, this one, and pull that out. And that is, okay, so that's wrong. That's 0.04 meters. I want that to be 0.25. So I'm just going to change that. So there you can see it's changed it straight away. The other dimensions don't really matter, but I can put them in if I want. So I can put in some vertical ones. So I can say from here to here and pull that out. So again, that's 0.2, that's fine. And again, from here to here and pull that one out, and that is 0.4. And again, that's fine. Okay, so that is my sketch done then. So I can go back to modeling, and now what I want to do is I want to create a surface from that sketch. So I'm going to go concept, surfaces from sketches. I'm going to click on sketch 1, and then I'm going to go apply, and then I am going to go generate here. Okay, so now I have my surface, which is turned up, my surface body. Okay, so now I am ready to move on to building my FE model from this geometry. So I can either close or minimize this window. First of all, maybe just no harm just to give it a quick save. and then close down that window, and then you can see the model is ready to go. So again, I can just double click on that to open that. So you can see mechanical is opened now, and I have my surface in here. Okay, so we'll just work our way down through this tree and make sure everything is okay. So the first thing, we have geometry, and the first thing when you click on geometries, you see here it's automatically defaulted to plane stress, which was fine in the last tutorial we did, which we played with a hole. We wanted plane stress. This time we wanted axisymmetric, so it's important that we click here and change that to axisymmetric. And then maybe just click on the surface body, and you'll see that structural steel is defined. So that's not what we want. We want to change that to my steel. So that's everything done in geometry. The next thing then is mesh. Okay, so again, what I'm just going to do here is I'm just going to let Workbench do its default mesh, and we'll see what that looks like. So I'm just going to say generate mesh. And again, not expecting too much from this. Okay, so again, that's a really bad mesh because we have basically the same size element throughout the entire problem. You can see we've only got one element across the thickness here. We've literally got three elements trying to span the curve there, which again, that's just not good enough. Okay, we won't get a good result with that. So we need to do something about that. So let's just click on mesh again, and let's just look at sizing. So actually, sorry, we just look above sizing for the moment, and we look at element size. So you can see the default element size is about 2 e to the minus 2 meters. Okay, so maybe what we just do is change that. So at the moment is 2 e to the minus 2. Let's put it in as 1 e to the minus 2. Okay, so that's our default element size now, and we can remesh that. That should be about half the size that they are here. Okay, so again, you know, a bit better. We've got a few elements through the thickness here. Probably not enough elements along the curve there. Okay, but what I'm going to do for the moment is go ahead with this and solve it and see what results we get, and then we're going to come back and we're going to put a better mesh on that later on. Okay, so we're ready to do our solution then. We can either solve now and then populate sorry, we can't solve now because we haven't applied our loads and boundary conditions. So let's go and put our loads and boundary conditions in. So first of all, let's put a frictionless support here on the bottom edge. Okay, so what that means is we want this line here to be able to move. All the nodes here can move along in the x direction, but they can't move in the y. So this is fixed in the y. So it doesn't stop this distance here from thinning, from getting thinner as we expand in the vertical direction, but it won't allow any of these points to move in the vertical direction. And then the next thing then is we need to put a load on the top. So we're going to put a force on this line on the top, and we're just going to change this to components, and the y component is 1000 newtons. Okay, so maybe just zoom out a little bit there just to see. So you can see we have our arrow. So I click on static structural, I have a frictionless support there, and I have my arrow up there. So I shouldn't need to apply my symmetry boundary condition here because it's on the y-axis. Okay, and I should see it as being axisymmetric. Okay, so now going back to what I was saying a minute ago, I can just solve now, or I can start to populate the solution information. So I'm just going to tell it what I want already. I'm going to say what I want you to show me total deformation. I want you to show me directional deformation in the y direction. I want you to show me stress, normal stress in the y direction as well, because that's what we're going to compare our results to. Okay, so now we're ready to solve. Again, it's a good idea to just do a quick save. So I click on static structural and I click on solve. Okay, so now my solution is done and I can take a look at my results. So the first thing I'm going to look at is always a good idea to look at the deformation. So let's look at total deformation. So it's saying the maximum movement of any point is the red region here, which is 5.3 e to the minus 7 meters. Very, very small which is good because I'm in the linear elastic zone here. I've applied a relatively small load to quite a sturdy piece of steel. I'm not expecting it to move that much. Again, we can always just check the deformed shape. Always a good idea just to do that. So we go to result here. So at the moment it's scaling it up by 3.9 by e to the plus 4. What we can do is we can show the undeformed wireframe. So just to show us, so that's the original shape there, the wireframe or the line around the outside, and that's our new shape. Remember, that's quite scaled up. If I put that to true scale, they're exactly the same. If I put it up to twice the auto scale, you can see it's very much exaggerated. Okay, or it could even go, 5 times the auto scale. Okay, so remember, the auto scale is just there to give you a bit of a visualization to help you see what's actually happening. So really, true scale or the auto scale is useful sometimes. So again, the auto scale is showing me there that it's expanded a bit up that way. So again, I can just go back to no wireframe or show elements, which is the usual one. Okay, so there's my elements. So the directional deformation then isn't that different to that. So it's 5.3 in the y direction. And if we look at our stress, our maximum stress is 6.23 e to the 5. So in other words, 623,000 pascals. Again, let's just go and look at our theory that we calculated and see how far off. So again, this is our problem definition, and our nominal load was that, and our theoretical load was 697. Okay, so we've got 623 and 697 is what we're aiming for. So we're in the right ballpark, but clearly there's a few things we could do with our mesh to get us closer to 697. So let's go back and take a look and see what we can do. So we're back in Workbench again, and we're going to go and we're going to remesh this. So rather than remeshing in here, what we're going to do is make a copy of this model. So we're going to keep this model as our original result, and we're going to go back into the project schematic and create a duplicate of it. So first of all, let's just close down that. Here we are in our project schematic, and what we're going to do is click on model and right click on model and go duplicate. So you'll see it'll create another version out here. Okay, so that takes a couple of minutes. I paused the video there rather than just leaving you hanging, so you can see it's created another version. So it's called a copy of static structural. Again, you can call that whatever you want. Maybe I'll just call it, let's just call it better mesh. Okay, so what you can see what's going on here is that the engineering data from our original model, again, maybe just call this original model, just so we don't confuse things. So the engineering data and the geometry from our original model are basically copied straight across to our new analysis. And now what I can do is I can change our finite element model here. So let's just open that up. Okay, so our model has opened up. You can see it hasn't solved because this is our new model. What I'm going to do is go into mesh, and I'm going to do, first of all, what I want to do is, our main problem with this mesh is we don't have enough elements along the curve here. Okay, so if you look in, we can maybe just zoom in here a bit, but you can see that, we're not really going to capture that curve with those elements there. Okay, there isn't enough of them along the curve. So what we want to do is force Workbench to actually put more elements when it encounters a curved region. So one of the ways we can do that is by clicking on sizing here, and you can see we have the curvature. Let's move this. We have curvature minimum size and curvature normal angle 30 degrees. So basically that's 30 degrees is how much it will allow an element to capture along the curve, if you like. So let's just first of all, let's just bring that down to 10 degrees to start with. Okay, and see what happens. So now it's telling me the mesh needs to be done again. So again, just click on generate mesh, and we should see some changes in around here. Okay, so now you can see that it's, you know, around the curve here, it's put a lot more elements in there. Okay, still maybe not the best mesh, but again, let's have a look at this one. Let's just see what this does. Let's give it a quick solve. So this model is easy to solve, and solves quite quickly. There's no harm in just checking out exactly what the effects of small changes are. If you had a larger model that took a long time to solve, you maybe would put a bit more effort into getting the mesh right before you issue the solve command. So again, let's just go straight to the normal stress. 644. So remember we're looking at about 6.7. I think it was 6.9, 6 something like that. Okay, so we're still really not getting that close to where we were. Let's go back and play with the mesh again. Let's bring the curvature angle down to 5. And then again, we'll go back and we'll change these sizes in a minute. But we'll just play with the curvature angle for the time being. Let's go generate mesh again. Okay, so now you can see we're getting much more refined mesh in the area where we need it to be refined. So this is getting to look a bit nicer because we have big elements out here where we don't really, where stress isn't changing that quickly, and then we have it slowly transitioning into smaller elements around here where we know that there's a stress is changing quite a lot. Okay, let's give this one a go, and this hopefully should be a bit better. Okay, so let's look at normal stress this time. 6.6. Okay, so still not up where we're expecting it to be. So let's just take a look here at what could we do to improve this. So let's just take a look at where stress. So stress is changing very rapidly in this region here. Okay, yeah, all in around here. Okay, there's not much happening here. There's not much happening down there. So it's this. Excuse me. It's this region here that we need to really concentrate on. Okay, and let's just try and get a little bit. Let's just try and get more elements in here. Okay, so let's go back to mesh. And let's just maybe reduce this. Let's just halve this. Okay, and try it again. So now it's made it smaller all over. Clearly, I mean, we didn't really need to do that. What we could do is go in and put some line sizing on here and bias these lines and make it so we had larger elements out here and getting down to this size in and around here. Again, let's just go with this for the time being and just see what happens. So again, just do a solve command again. And this time our normal stress. So we're still getting 6.6. Okay, we're not really improving that. We'll give it one more go. Okay, so you can see here maybe that where we have the stress changing here, maybe it's changing a bit too rapidly. Let's just have a look at that. Let's go in here. So we've got actually quite nice smooth curves here. Okay, so we're not seeing too many jagged edges, maybe a little bit there. Okay, so maybe what we could do is maybe remesh around here somewhere. The other thing that's important to do is maybe it's a good idea to have a little bit of a probe in there. So if I click on probe here, okay, that will show me whatever result I'm looking at. It will show me the result at that point. Okay, so again, here we have 6.5, 6.606, 5.8. So that's our high stress right there. Okay, kind of where the curve goes into the line. Okay, so again, let's just come out here. So maybe we might try and go in and put some line divisions on there and see what effect that has, or if that helps. So what I'm going to do this time is go into mesh. I'm going to insert a sizing, and I'm going to pick this line. I'm going to go apply, and at the moment it's set to element size. I'm going to set it to number of divisions, and it had approximately 30 divisions on it, so I'm just going to put that up to 50. And we're just going to do a remesh then. So you'll see now I've gotten, if you compare this side to that side, for example, you can see that I've gotten much more divisions here. So these ones they're all the same size, and they're closer in size to the ones around the curve than the old size would have been like this. So again, let's just have a zoom in just to see what I'm talking about. So again, the old element size would have been that over here. So these ones are about maybe, I don't know, 2/3 of that. You can see they're closer to what I want to get to in there. Okay, so we'll just see if this has made any difference. Again, we'll just do another solve, and we'll probably leave it at this one. Not expecting too much of a difference. Okay, so our stress is, yeah, still 660, 6649. So we were expecting about 69. We didn't get that. We got around 66. So what's the reason for that? Well, the FEA in this case is probably more accurate than the stress concentration factor predictor. The stress concentration factor is a relatively crude theory. The ideal thing here would be to have some experimental results to compare to. We're in the same ballpark. You know, we're getting 665,000 roughly. The stress concentrator predicted 69 something. Okay, so we're 30,000 megapascals out, 30,000 pascals out, which, you know, 0.03 megapascals, which, given what we're doing here, isn't too big a deal. Okay, so I think, and you'll also notice that as we've remeshed this more and more, our result has changed less and less, which is a sign of mesh convergence. Again, we'll talk about that in another video, but essentially what we're trying to do is, you know, refine our mesh until our result doesn't change anymore. And I think we've done that. We've, you know, we haven't gotten any better. We've gotten 6.6 here, and if we maybe just go back and take a look at our previous model, so maybe just close this one down and look at our first model. So again, that's still there, which is a good thing about doing it in this way. We'll just open up the original model again. So this is our original model with our original mesh. You can see we were getting 6.2, and by our remeshing we got up to 6.6. So we got closer to the theoretical result, but for all our remeshing efforts we didn't get quite up to 6.9, which is what the theoretical result was showing us. What we did show though is we're getting a convergence curve. So maybe just talk very briefly about what that is. So this is just looking at my book, Practical Stress Analysis with Finite Elements, and we're in chapter 7 in there, and we're talking about modeling and meshing, and we're looking at mesh convergence. So what mesh convergence really is if you look at this figure here, we'll maybe just zoom in here and take a look at that. What we're trying to do with mesh convergence is we're increasing the number of elements each time. So maybe our first mesh, we start off here. In our case, maybe we had something like, I don't know, 200 or 300 elements. Then we maybe up just to 500 elements. Maybe we went up to 1,000. So as we're doing that, we're getting closer to the exact solution. Okay, so in our case, let's say the exact solution was our stress result predicted by the stress concentration factor, which was our 697, I think it was, 1,000 pascals. We started off at, to be fair, we probably started off up here somewhere. We started off at 62,000, then we got 64, 65, 66. So you can see what's happening is that as you increase the number of elements, if we started off with a really crappy mesh like the one Workbench tried to make us start off with, we'd probably be, you know, maybe half of the exact solution. As we increase the number of elements, what's happening is this convergence is happening. So we're not getting an improvement in accuracy as we were earlier on. So from going to, let's say, 500 to 1000 elements, you might be getting a 50% increase in our accuracy, but up at the end there, when we were doing our remeshing, we were going from maybe 2000 to 2100 elements. You can see that we're only getting a 1%, 5% increase in accuracy. So once we get to a certain point where remeshing or adding new elements doesn't change our result, what we can say is that our mesh has converged. So any more refining of our mesh won't really affect our results. Okay, it's not going to make the result any better, and that's the point we're looking for. Once we've done that with our finite element model, that means we can have reasonable confidence in the mesh. Normally it's very good to have an exact solution to converge that to, so like an experimental result or something like that. Here the best we had was stress concentration factor, which again is quite limited. It is simple theory. Okay, so that's it for today. So we've built our axisymmetric model in Workbench, and we generated an axisymmetric finite element model. So that is the end of our axisymmetric analysis of the stepped circular shaft in ANSYS Workbench. So again, as always, there's a lot more information on this type of analysis and the rationale for this type of analysis and the theory behind this type of analysis in the book. So again, I would advise that you go and get a copy of the book and read that. And again, I hope you found this tutorial useful. If you have any questions or comments, then please comment below and I will try to get back to you. If any ideas for other videos, again, just mention them in the comments below and we'll try and get to those for you. Alright, thank you very much for watching.